Hello. Today I'm going to talk to you a little bit about the history of nuclear fission, the process of nuclear fission, and some of the technologies associated with it. Nuclear fission of heavy elements was discovered on December 17, 1938 by Otto Hahn and his assistant Fritz Strassmann. The actual process that occurred was theoretically understood in January of 1939 by Lise Meitner and her nephew Otto Robert Frisch. The science of atomic reaction and nuclear fission was developed from 1895 to 1945, much of the progress happening in the last 6 of those years. From 1939 to 1945, most of the understanding of nuclear fission was used to try and create atomic weapons to gain an upper hand in World War II. And only after World War II ended did researchers move their focus to try and understand and develop sustainable energy through nuclear fission. But before we try to understand atom bombs and fission reactors, we need to understand the fission reaction itself. The short-range nuclear force tends to overcome the repulsion force of protons in the nucleus for small atoms. But as more protons are added, the repulsion force begins to overcome the nuclear force, keeping the atom together. This is what causes atoms to decay, emitting either an alpha particle, a beta particle, or gamma radiation, depending on the element. For example, uranium-238 has a half-life of 4.5 times 10 to the 9 years, emitting a beta particle when it does decay. Another way for unstable atoms to become more stable is to fission. To understand the exact reason atoms fission requires a detailed understanding of the nuclear spin of subatomic particles, the nucleus's tensor components, and the momentum of each individual nucleon. For the purpose of this explanation, simply understand that the ratio of neutrons to protons is too great in atoms that are unstable. The fission reaction of uranium-235 looks like this. The bombardment of a neutron with the uranium initially increases the atomic mass of the uranium, making it even more unstable. This increased instability causes the uranium to split into 2 different fission fragments that are completely unstable due to the number of neutrons they carry. Note that the fission reaction isn't clean. The total number of mass in the 2 fission fragments can vary depending on specific conditions during each individual fission reaction. The heavier fragments usually have mass numbers between 130 and 145, while the lighter fragments usually have mass numbers from 85 to 100. It is these 2 fragments that release additional neutrons to become more stable. This graph, showing the ratio of protons to neutrons, visualizes the stability of uranium and its fission fragments and gives clear representation that the fission fragments are themselves unstable and require emission of additional radiation to become stable. This radiation to stabilize the fission fragments are the neutrons that will cause additional fission reactions of uranium-235 seen during sustained nuclear fission. It is also important to note that not all isotopes of uranium cause fission chain reactions. For example, uranium-238 is less stable than uranium-235, but only produces neutrons with critical energy that isn't high enough to break the critical barrier of other uranium-238 nuclei to continue reactions. Thus, such reactions are called fissile reactions. Not even all the neutrons that bombard uranium-235 cause fission reactions. Only about 85% of the neutrons that hit uranium-35 actually cause fission reactions, while 15% of the time the collision simply creates the deadly gamma radiation we see in nuclear fission. Now we're going to talk about applications of nuclear fission. One application is the atom bomb. The reaction of a nuclear bomb starts off by igniting the primary fission fuel inside the bomb shell. This reaction causes the foam surrounding the secondary fission fuel to heat up and become a plasma, which in turn ignites the secondary fission fuel. Looking for more progressive forms to utilize fission, we will now look at the nuclear reactors and how they obtain energy from fission. Common in today's use are light water reactors. These reactors use normal water as opposed to heavy water, both as its coolant and neutron moderator. The water is heated in the reactor vessel and used to turn turbines that produce energy. This form of nuclear reactor is the cheapest and simplest form to use, and it's why it's favored by countries all around the world. But it's far from the safest or most efficient form. Another way to utilize nuclear energy is to use thorium-based nuclear power. In this sort of reactor, thorium is enriched to make uranium-233, which is used in fission. Thorium is much easier to obtain than uranium-235 for many reasons. For one, it's much more abundant, making it more available than uranium-235. It's also a lot safer to obtain over uranium, or even coal for that matter. It's also much more difficult to use the byproducts of thorium reactors to create nuclear weapons. The waste of thorium reactors is less toxic and only remains radioactive for a few hundred years, as opposed to the tens of thousands of years it takes for light water reactor byproducts to decay. Thorium reactors can also be made with a design to prevent virtually all meltdown situations by draining the fuel in underground tanks in case of power failures or uncontrollable temperature rises. So understanding the complex physics of fission reactions has led us to our most devastating weapons and many forms of clean, sustainable energy. Continuing to gain knowledge over such detrimental forces of nature is required if we were to use it to humanity's benefit and not its demise.